What if a particle does not travel from point A to point B through one clean, simple route, but through something stranger? Have you ever imagined that the smallest things in the universe do not move like tiny bullets at all? Today, we are looking at one of the most famous and unsettling ideas in science, the double-slit experiment. And by the end, you may see reality itself a little differently. The double-slit experiment sounds simple enough. You take a source that fires tiny particles like electrons toward a barrier. That barrier has two narrow openings, two slits. Behind it, there is a screen that records where those particles land. If particles behave the way common sense expects, each one would pass through either the left slit or the right slit, then hit the screen behind it. You would expect two bright bands on the screen, one behind each slit. That is exactly what you would predict if reality worked like little solid objects moving through definite paths. And sometimes that is exactly what happens. But when scientists perform the experiment under the right conditions, something far stranger appears. Instead of just two bands, the screen shows an interference pattern, a series of bright and dark stripes. This is the kind of pattern waves make. You can see similar patterns with water waves. When two wave sources overlap, some parts reinforce each other and become stronger, while other parts cancel each other out. The result is not two simple lines. It is a repeating pattern of peaks and gaps. So when particles create an interference pattern, science is forced into a very uncomfortable question. Why are particles acting like waves? This is where the experiment becomes famous and weird. If you send many electrons through the two slits, one by one, slowly, with enough control to make sure they are not colliding with each other, the interference pattern still builds up over time. One electron lands on the screen, then another, then another. At first, the dots seem random, but after enough electrons arrive, the same wave-like pattern emerges. That means each individual electron contributes to a pattern that normally belongs to waves. It is as if each electron somehow behaves like a spread-out possibility instead of a tiny marble. And this leads to the core idea. The experiment suggests that before a measurement is made, a particle may not be committed to one single path in the way our intuition expects. One useful metaphor is to think of a particle not as a tiny rock, but as something more like a cloud of possible routes. Not a physical fog in the ordinary sense, but a mathematical spread of possibilities. That spread evolves like a wave, and when there are two slits, the wave-like description seems to pass through both openings. Those possibilities interact with each other. Some possible routes reinforce, others cancel. That interaction shapes where the particle is likely to appear when it is finally detected. In that picture, the particle does not simply choose one path early and then follow it all the way through. Instead, quantum theory describes a range of possible paths contributing to the final result. Another way to understand it is through the idea of a map. Imagine you are not tracking a traveler with a single line on a GPS. Instead, your map shows many possible routes glowing at once. Most of them fade, some combine, some interfere. Then only when the journey is finished do you see one actual arrival point. That is closer to the strange logic of the experiment. The particle is not behaving like a classical traveler with a fixed route that was always there waiting to be discovered. It behaves more like a system whose possibilities matter. A third metaphor is a filter. The slits do not merely act like two doors, they shape the possible behavior of the particle. By changing the experimental setup, you change the pattern of possibilities itself. And that matters because quantum physics does not just describe objects. It describes how outcomes are structured by the conditions of observation. This becomes even stranger when scientists try to measure which slit the particle went through. If detectors are placed at the slits to find out whether the electron passed through the left slit or the right slit, the interference pattern disappears. Suddenly, the result looks much more like ordinary particles choosing one route. Now the screen tends to show two bands instead of a wave pattern. That does not mean human consciousness magically creates reality. It means that measurement changes the physical situation. When the system is forced into a setup that reveals path information, the wave-like interference is lost. In simple terms, when nature is arranged so that the path becomes knowable, the behavior changes. That is one of the deepest lessons in modern physics. The way reality behaves depends on what kind of question the experiment is structured to ask. This does not mean reality is fake. It means reality at the quantum level does not follow the visual logic of everyday objects. We are used to thinking that things are always somewhere, moving in one direction, on one path, whether we look or not. The double-slit experiment warns us that this picture may only be an approximation that works in the large-scale world. At the smallest scales, nature seems to operate with a richer rulebook. One implication is that particles are not just tiny versions of baseballs. They belong to a quantum world where probability is built into the system itself. The future is not always a hidden fixed story waiting for us to uncover it. Sometimes the theory only gives a landscape of possible outcomes and the probabilities connecting them. A second implication is that observation in physics is not passive. Measuring is not like opening a curtain and peeking at a scene that was fully settled in advance. Measurement is an interaction, and interaction affects what can happen next. That changes how we think about knowledge itself. A third implication is that the universe may be less like a machine made of miniature gears and more like a structure of relationships, possibilities, and constraints. What matters is not only what something is, but how it is allowed to behave within a given setup. That is a very different view of nature. A fourth implication is practical and psychological. Our intuition is not a perfect guide to truth. The human brain evolved to throw spears, avoid danger, recognize faces, and survive in the visible world. It was not built to naturally understand quantum systems. The double-slit experiment is a reminder that reality does not owe us comfort, and that can actually be freeing. It means confusion is not failure. Sometimes confusion is the first honest response to something real. A fifth implication is philosophical. If particles do not simply choose one path in the classical sense, then certainty may not sit at the foundation of existence in the way earlier generations imagined. Maybe at the deepest level, reality is not a single rigid track unfolding like clockwork. Maybe it is a structured field of possibilities that only becomes definite in specific interactions. That idea has shaped physics, technology, and philosophy for more than a century, and it is not just abstract. Quantum mechanics, the framework built from experiments like this one, helps explain semiconductors, lasers, modern electronics, and much of the technological world around us. So the double-slit experiment is not just a strange thought experiment from a textbook. It is one of the clearest windows into how the universe actually behaves, and its message is still shocking. The world beneath everyday life is not simply made of tiny objects taking tiny paths in tiny spaces. It is made of something stranger, something that behaves like possibility before it behaves like fact. So what does the double-slit experiment really show? Not that particles think, not that humans create the universe by staring at it, but that at the quantum level, reality seems to resist the simple demand that everything must always have followed one ordinary path all along. And maybe that is the real lesson. The universe is under no obligation to look intuitive. Lucid order. Question everything.